Good afternoon, everyone. Thanks for coming in. Hopefully, you all had a chance to take a break, grab some lunch. AI is solving a lot of problems. I'm hoping one of these days it will solve the post-lunch sleepiness problem. So with that, my name is Shan, Kulandaivel, and I lead the product management team for Google Cloud. I have a couple of co-presenters with me. I'll let them introduce themselves before we jump in.
Hi, Reza Rokni. I'm developer advocate working for the Dataflow team at Google.
Hi, I'm Cung Tran. I'm a ML engineer from Etsy.
Okay, I figured out how this works. Fantastic. Thanks, gentlemen. I'll call you on stage for your sections. So before I jump in, let me quickly give you an overview of what we plan to cover today. I'm hoping to kick it off with a little bit of an overview of the kind of business problems that users like you are interested in solving. We call them real-time intelligence. You may be calling it with a different name. So we'll do a little bit of context setting, talk through those kind of business problems and why it matters. I'll then give you a high-level overview of the kind of data architecture you need in place to enable those use cases. I'll then have Reza come over, talk through in detail about many of the capabilities that we have in the product that will help you implement those use cases. We'll then have Cung join us on stage. We'll do a Q&A. Totally unrehearsed. You'll have to believe us when we tell you that. We'll do a Q&A where Cung will share his experience at Etsy implementing these use cases. And then finally, time permitting, I'll do a quick roundup of some of the latest and greatest capabilities in Dataflow. So with that, let's get started. So let's talk a little bit about the use cases. So when I talk to users like you, the potential that streaming data and machine learning has in being able to drive transformational changes in your business is abundantly clear. If you think about it, every interaction that your microservices have, every interaction that your IoT devices have, the engagement that you have with your users, maybe your employees, vendors, suppliers, so on and so forth, creates a lot of meaningful data. If you have the ability to gather all of that, get meaning out of that data, and drive insights, now you have the ability to build new transformational business capabilities or go build new delightful experiences for your end users that puts most relevant information and actions at their fingertips when they need it. We can see the examples in all industries and verticals. I have customers in healthcare that are implementing use cases like real-time patient monitoring, fraud detection when it comes to insurance. We are all familiar with use cases on the retail side, be it things like cart upsell, product recommendations, or customer 360. And on the other end of the spectrum, something like manufacturing and IoT, which in many ways, in fact, kicked off the streaming data revolution. You have use cases like predictive maintenance, supply chain management, so on and so forth. So we've talked about the use cases. Let's talk a little bit about the kind of data architecture that you need in place to support these use cases. Traditionally, a lot of data analytics and machine learning was batch-driven. You ran batch ETL processes. Maybe you ran it once a day, once hour. You got data from your operational systems, your transactional systems, mostly SQL databases. You ran an ETL process, took that to your data lake or your data warehouse, and then you had machine learning feature extraction happening, batch training happening, batch prediction, and so on and so forth. What this allowed you to do is get insights from batch data or historical data, do predictions, store them up. Maybe you had a NoSQL database where you had all your predictions stored. And then at the time of serving, you had your serving systems look that up. Now, this is going to continue to exist, right? There's a whole bunch of use cases that needs this architecture. This architecture is sufficient. We are going to continue to see this. But for the kind of real-time use cases that we talked about in the previous slide, you need to move to an architecture where you're able to do things like real-time features. Some call it online features or streaming features. You need to be able to do, depending on the use case, real-time predictions or real-time inferencing. So let's talk a little bit about how you get there. Hopefully by the end of this, I would have figured out which is move forward and which is backwards. OK, so the first step for streaming is, of course, obvious. You need to have streaming data in place. right? No surprises. We're not going to go into the details of the messaging systems. I suspect a lot of you are familiar with things like Cloud PubSub, which is our partitionless cloud scale messaging platform. You also have Kafka. Anyway, the first step is to get your upstream systems to ingest data into one of these, right? So once you have data in, PubSub or Kafka, you can start to do a lot of interesting things with it. Now, very similar to the batch ETL world, where the data coming in from your transactional systems is not ready for analytics or machine learning, the same is true for streaming data as well. Right? You need a mechanism by which you're able to take that raw data in your streaming system or in your messaging system, process it. You may be enriching it, just cleaning it, or conforming it to a specific schema, or you're doing more interesting things like streaming, feature extraction. But you need a stream processing platform. In some cases, you could go roll your own system, but there is a lot of underlying plumbing and infrastructure that you need to take care of it. Products like Dataflow and open source products like Apache Flink solve that problem for you. These platforms give you an SDK, higher level SDK, a MapReduce based SDK that allows you to just focus on the data processing task at hand and not worry about the underlying infrastructure. Okay, so we've solved that problem. We now know how to process the stream and extract information from it, do things like enrichment. All right, go for it. Is that sufficient, right? So now you've got data, you can make sense of that data. Now you need to figure out how you go from processing to intelligence. Now, there are a lot of things that go into that, but there are 3 things that we've observed in working with a lot of customers. So one, even when you're doing streaming machine learning, you have a need to leverage batch data. Now, that may be just for backfilling things. It may be for you're filling gaps in your data. In some cases, you're enriching your streaming data. And in other cases, your machine learning use case may need a combination of streaming features as well as batch features. The second challenge that we've seen is you need a scalable way for you to incorporate inferencing into your streaming data processing. You may be doing local inferencing or remote inferencing. There are some trade-offs involved. We are not going to go into the details of that today. I do have a couple of use case or architecture slides that I'll show you, but there are some interesting trade-offs involved, and we've seen the need where customers want to start with local inferencing, but move to remote predictions and go the other way as well. And then lastly, one of the defining attributes of real-time intelligence is the ability to take actions without having humans in the loop. Right? Traditionally with BI, you got all the data, you got analytics, and then you had a dashboard, you had a human look at it, maybe once a week, once a month, and took decisions. With real-time intelligence, you want to get to a state where the machine is making getting insights, making decisions, and activating that. Now, that means that you need to have an ability to have those insights reach your downstream systems. It could be, again, a messaging system. It could be your serving system or your transactional system. So that's where something like Dataflow comes into play. Right? I suspect a lot of you are familiar with Dataflow, but for those of you that are not familiar, I'll give you a quick overview. Dataflow is Google's cloud-native data processing technology, both for batch and streaming data processing. It uses something called Apache Beam, which is the SDK for defining your streaming and batch data pipelines. Both of these are based on a technology called Flume that Google uses internally for all of its big data processing needs. Anyway, so Dataflow is a serverless service that executes your streaming and batch data processing pipelines. Apache Beam SDK gives you and Cung will cover some of this on why they chose Apache Beam and Dataflow, gives you a developer-friendly SDK that allows you to define your data processing pipelines. There are a lot of things about these two that we don't have time to go into, but I want to highlight 3 capabilities that makes it uniquely suited for real-time intelligence. The first is the fact that both the SDK and the servers support unified batch and stream processing. Reza, when he talks through his section, will show you some code samples that show how it is easy to switch from batch to streaming. But you have one SDK, one technology to do both batch and streaming. And more importantly, you could have one pipeline that handles both batch and streaming data. The second aspect, I talked about how you need to be able to connect to your downstream systems to activate insights. So that's where having robust support for bidirectional I/O comes into play. And then lastly, which is what Reza is also going to talk about in detail, having a set of out-of-the-box ML capabilities means you're not reinventing the wheel. You're not going through the toil of writing a lot of boilerplate code that uses best practices and things like that. So you have out-of-the-box capabilities that makes it easy for you to quickly get started and just focus on the core business logic on your side. So this is how, if I were to plop Dataflow into the diagram that we saw earlier, this is how it would look. Now, this may be a little bit abstract. So let's double-click and look at like few actual examples that customers have implemented. So this is from a telecom customer of mine that has implemented a network intrusion detection use case based on using anomaly detection techniques. So to do that, they ingest logs, network logs from their on-prem systems. Their real-time data comes in through Kafka and PubSub. Their historical data comes to Google Cloud Storage. They have a Dataflow pipeline that then ingests both of that data, does things like feature extraction and real-time predictions. And in this case, the model was local to the Dataflow job. They also leverage something like Cloud DLP API so that they can de-anonymize or anonymize the data to remove PII information from their logs. To meet regulatory requirements, they allow to remove PII from anything that powers their ML algorithms. So given the flexibility of Dataflow, they are able to do that. Now, contrasting, here's a different example where the customer was doing fraud detection. In this case, they used a boosted trees model that was hosted in Vertex AI. For various reasons like flexibility and being able to manage the model independent of the data pipeline, the model itself was hosted in Vertex AI pipeline, and the Dataflow job, or the Dataflow pipeline, called into Vertex AI for doing predictions. Now, with that, I'm going to have Reza come over, join us, and walk through some of the capabilities in the product that is going to make it a lot more easier to build use cases like these.
Thank you. Let's see if I can figure out the clicker. No, wrong way. There we go. Hey, everyone. Thanks, Shan. So let's take a look at the role of Dataflow in this flow here. The first thing the Dataflow in the middle of the service has to do is it needs to read from our source. We will then need to do some pre-processing of that data, and then we will pass that pre-processed data to a machine learning model. In the first part of this talk, we're going to mainly concentrate on where you have got a pre-built model that you're going to pull onto the Dataflow service for local inference. Next, we would normally have a post-processing process, so you would take the inferences, maybe join it with some other information before you activate it at the other end. Now, the things that we're going to need to do for this, obviously there we go. Obviously, the Dataflow service, which is a fully managed environment, which is spinning up the workers and executing the work that we described. For that Dataflow service to know what to do, you're going to have to build your pipeline within its SDK, which uses the open source Apache Beam SDK. For those of you who may not be familiar with Apache Beam, we're going to spend a couple of minutes just looking at Apache Beam and how you would build a pipeline. So Beam relies on a few core primitives that lets us build up our pipeline. First of all, it's a P collection, a parallel collection of immutable objects of the same type. This is the data that we are going to do our transformations on. For the transformations themselves, we have our P transform. Parallel transform allows us to process the data within the P collections, creating new P collections. Of course, this is all done in parallel and at scale. Finally, we need a way of putting all this together. For this, we're going to use the pipeline primitive. So here, the pipeline is a directed acyclic graph of computation, which tells the system how the P transforms and the P collections are interacting with each other. To bring it to life, we're just going to put together, first of all, a simple batch pipeline, and then we'll make it streaming. So let's imagine that you have physical stores and some online stores, which both generate files that we want to do some processing on. There's some sales information, we want to do some sales analytics. So first of all, we would need to read those files. To do that, we're going to make use of the Python SDK here. The P designates a pipeline object, and the pipe operator means apply this transformation to the pipeline. So here we're applying the read from text transform to the pipeline, generating our store sales and online sales P collections. Next, we're going to use a primitive from Beam to bring it all together. So this is the flatten operator. Essentially, this takes two P collections with data types of the same type and brings them together into a single P collection. Next, we're going to do our analytics. Now, the details of this doesn't matter. Essentially, it's just going to find the top sales values. After we've done our analytics, we then want to output the results to a sink. Here, we're going to make use of BigQuery sync, which is BigQuery IO write to BigQuery. So with this, we've built a batch pipeline. How do we now change it to a streaming pipeline? As Shan said earlier, Beam was from the outset built to be both batch and streaming, so we don't have to touch our business logic, but we do have to add one more primitive, and that's the window primitive. So because the data is continuously arriving, we need to actually know how to do the computations, when to output a result, and for that, we use the window primitive, which essentially subdivides a P collection into timestamps. So let's change our pipeline. So now at the top, rather than reading from files, we're going to read from Google Cloud PubSub. Of course, this could be Kafka. So we now got a continuous stream of information flowing through. And if you'll note, just before our business logic, we've applied the window into transform. This is just creating those fixed windows of 10 seconds, which means we're going to get continuous output every 10 seconds. That is then written to BigQuery. OK, so now how do we turn this piece of analytics here into a machine learning model? So we've built a trained model, and we now want to use that for the inference rather than simple statistics here. Well, if we were to do this with the primitives of Beam, and there are many more than the ones I described, of course, and you wanted to do it in production, there's actually quite a lot of work to do. So first of all, given model sizes, we need to make sure we share them efficiently across the threads on the worker. This is a streaming pipeline. We need to make sure that bad data is not only preserved by using a dead letter queue, but also doesn't clog up your streaming pipeline. We need to make sure that any pre and post processing that is done on the model is encapsulated within your model object so you don't get training serving skew. We need to make sure that when a new model arrives in your streaming pipeline, it is quickly updated. So all of this sounds like a lot of code and far more work than just a few lines in your streaming pipeline. Luckily for us, our Dataflow engineers have been working on adding things to Beam known as a turnkey transform. The idea behind a turnkey transform is rather than you as developers having to take building blocks to generate your goal, we provide a single line of code, a single transform, and you provide configuration, which is the thing that you want to do, and we take care of all the productionization. So the one that, so rather than having to write hundreds or even thousands of lines of production code, which of course then needs to be maintained, documented, tested, you now do a single line. And the one that we have first launched is run inference. No surprise given all the excitement around machine learning and in this space. So run inference with this single line of code, we have done encapsulated all of the things that I described in the how to productionize a model within the Beam pipeline. And you as a user use that one line plus providing a model handler. What is the model handler in this code? Well, it is simply configuration. This is an example of one. This model handler is telling us that the model you are going to use is a PyTorch model, its location in a Google Cloud Storage bucket, and some other information that's pertinent to that particular model. Since adding run inference to Beam, we've been continuously working. It was added early in mid last year. We've been adding features to it. I can't go through all of the features that are available, but I'll cherry pick a few. One is support for lots of frameworks. So obviously this is very key, and we are adding more, and there is also something known as a custom model handler if your particular framework isn't on this list. Another thing we've added is support for working with model repositories. So if you are using something from TensorHub or Hugging Face, the configuration you pass in this case, Hugging Face Pipeline Model Handler, gives us the ability to know what your intent is to be able to pull the model onto the workers. Next, this is my favorite feature, is streaming updates. So in a if you're training your machine learning pipelines in your MLOps systems, you're going to be continuously updating them, you're going to be making them better, and you want them to be deployed to your streaming pipeline without having to pause or quiesce that pipeline. So with this feature, when a new model arrives, it gets hot swapped on the Dataflow service for you without having to pause the pipeline at all. It supports two modes. One mode, it's looking for the file location. If the file location, the file changes, it's going to pull that model in. Another mode is an event-based mode, where, for example, you'll have in your MLOps system where you usually have a pusher component. Your pusher component can signal into the system that a new model is available, and it will go do the necessary to pull that model from, for example, the Google Cloud Storage bucket. Okay, so with these pieces, we can actually now do inference with very little code for our pipeline. One of the things about this particular pipeline is there's one model, and it's a very synchronous flow, which is, of course, some use cases, but many use cases are far more complex. So I had the great privilege of working with the very clever engineers at Spotify. And here, and this is in the public domain, in this blog, we go over how there are many machine learning models being used and different frameworks. So in the single pipeline, they're using PyTorch, they're using TensorFlow to actually achieve their goal of their business. Now, how do we use run inference and the Beam pipeline object to actually build these complex flows? So let's take this spaghetti. Well, pipeline, it really is spaghetti, right? If we imagine each one of these blue boxes is a model, the piece of data needs to run the gauntlet of all these models before it becomes useful to us. How do we do this? Well, if you look at this, there's a couple of interesting characteristics when we decompose it. First, all of the arrows are pointing one direction. Therefore, it's a directed acyclic graph of computation and fits in with our pipeline object. Second, you'll notice that actually there's only two patterns that are continuously being repeated. The first pattern, given a piece of data in our P collection, we want that data to have inference run against it against two different models. Well, you'll notice on the code on the right, there's very little to do. To our pipeline object, we simply apply two different configurations for run inference, and we can achieve this branching. The next piece is sequential models. So here, the data is being passed to model one. The output of that is then being sent on to another model. For example, you might be extracting text from voice, and then you want to do some sentiment analysis. Usually, the output layer of the first model is not in the right shape for the input layer of the second model, so you usually put a mapping function in between. So here we have, again, on the code on the right-hand side, very little code needs to be written to describe this path. And if you repeat this, you're going to get back to that complex spaghetti we saw in that first slide. So, of course, with inference, especially in a streaming system, latency matters. Even in a system where you can tolerate 1-2 minutes of latency, in a streaming system, the service rate of the transform that's doing the inference needs to be able to keep up with input. Otherwise, you're just going to get continuous backlog. So often you're going to make need use of an accelerator. And again, with the Dataflow service, I really haven't learned how to do this. I'll go forward. This is also straightforward. We provide an option that we pass in on pipeline creation time, as well as a custom container that contains all the dependencies that you have for your images. And this will install all of the NVIDIA drivers on the worker, as well as the NVIDIA GPU for you. We also work very closely with NVIDIA. We've enabled NVIDIA MPS, which allows for more efficient context switching when multiple Python processes are vying for that GPU time. Again, if you imagine in this streaming system, the GPU is in the middle, it's getting talked to by a lot of Python processes that are pulling in work as they go forward. The other exciting thing, so up until this point, we have been talking about models that we are pulling onto the Dataflow worker for local inference. What if you are using a great service like Vertex AI online predictions, which brings in all of the simplicity, flexibility, and assistiveness for that product's ability to deploy machine learning models for you? Well, happy to announce that as of Apache Beam 2.50, which is going to be released in the next few weeks, we have a new model handler called the Vertex AI model handler. Again, this allows you to make use of run inference, but now, with a few lines of code, you're connecting your Dataflow service to Vertex AI online predictions with no effort. And we can see customers making use of this in mixed mode as well. So imagine you have a small model that you use earlier on in your pipeline, like an embedding model or something like that, and the next call in that pipeline, you're making use of a very large model. So there you will mix the local inference with the remote inference for the best in breed of your pipeline. So with that, there's quite a couple of resources here for you. You can actually go on these links that are fully working code lab examples for all the things we've talked about today. And with that, I'm going to pass over to Shan.
Thank you, Reza. OK, fantastic. Do we have audio here? OK. Cung, I know we did a little bit of an intro. Can you tell us a little bit about yourself, what you do, and your Etsy, and maybe we'll kick it off with that.
Yeah, so I'm a ML engineer on the search ranking team at Etsy. Etsy is a global marketplace for unique and creative goods. You can buy everything from like handmade earrings to clothing to even furniture. So on my team, we train and deploy models to rank items on search result pages. So basically, when you type in a search query and you get a bunch of items, when you see some things at the top and some things at the bottom, that's what my team's responsible for. And we train our models using TensorFlow, and we build our pipelines on Vertex AI with Dataflow.
OK, that's great. Can you tell us a little bit about sort of your, the key business priorities and sort of the path that you've taken so far?
Yeah, so ranking is pretty important for search pages. A lot of users only really check the first few pages, so getting your ranking right is the difference between someone bouncing or converting. So you really want to make sure that you get this right. So one really simple way to do it is something called TF-IDF. It comes bundled in with a lot of open source search engines like Solr. And this basically, what this does is this scores each item in your search result set. So when you type in a search query, it checks how many times those query terms appear in the object. And it gives also a little bit more weight to rare items, or to rarer words, less common words. But this is a pretty simple scoring mechanism, and it's really easy to game. There's something called keyword stuffing. So you might have gone on a website before and you noticed like a product title had like 100 words in the title, because the manufacturer or seller is basically just trying to like put in as much as they can so that they can get in to as many search results and for as many searches as possible.
I deal with that every day in Amazon.
Yeah. So we really want to look outside of this realm of exact text matching and optimize like for both the relevance but also the likelihood of a customer actually buying an item. So luckily, we have a lot of search sessions and we log like what people search for, the items that we show them, the product titles, the prices, the review ratings, things that users have bought in the past, and so on. So we have terabytes of data per day. And when you have all this data, you know someone in the room is going to bring up, let's use ML.
OK, very cool. So you said ML. What techniques do you use today? And maybe if you can give us a sense for what you've explored, what you use today, and more importantly, bringing it back to the topic of the presentation, how that has influenced your data architecture.
Yeah, so our architecture for our model has changed a couple of times over the years. We actually built our first ML model in 2017, and for first ML model for ranking in particular. And we just started off with a simple linear model, and we used PySpark for our feature engineering, which, for those who don't know, feature engineering is just taking your raw training data, then prepping it for input to your model. So yeah, we used PySpark and some in-house libraries for that. As we started to put more investment into the ranking model, we decided to switch to a boosted tree model, which In 2019, when we switched over to this model, was kind of the state of the art for ranking at the time. And through many A/B tests of our models, we were seeing increased engagement and increased conversion. But from the development side, for both our linear and our trees model, we were kind of reaching a point of diminishing returns. We were running out of ideas on how to improve the model itself, and we ended up just doing more and more feature engineering to try to improve the performance of these ranking models. So lucky for us, around 2019, 2020, deep learning has become more popular in the ranking space, and there are papers being published like every year on on companies figuring out how to use deep learning in their ranking models. So this was a good time for us to also start investing in deep learning. And in 2021, that's when we started to put a lot more time into actually investigating this. And while we were making this switch, we decided to relook at our pipeline and make some changes in our architecture. So we actually decided to go with TensorFlow for our model training. It's just a really mature ecosystem for both training and deployment to production. And we also decided to switch off of PySpark onto Dataflow for our feature engineering. Dataflow has a lot of integrations with TensorFlow that makes it easy to work with. And also, some of the other benefits of moving to Dataflow was, I don't know if anyone's ever managed a Spark cluster before, but it can be very opaque to people who don't understand or people who have less experience with Spark. But with Dataflow, our developers could just focus on actually writing Python code and how the data flowed from one place to another. And in 2022 is when we were actually able to launch our neural ranking model as our baseline model in production.
Yeah, very cool. That goes back to the code samples that Reza was showing on screen, right? How easy it is to express your business logic with Beam.
Yeah.
Very cool. So how does your data architecture look like today? We talked a lot about your ML, but walk us through your the overall architecture for data today.
Yeah, so I have a pretty simplified diagram of our pipeline on the slide here. And basically, all of our training data is stored in GCS or Google Cloud Storage. And we use TensorFlow Transform for our feature engineering. So TensorFlow Transform is a library that runs on Dataflow, and it allows you to run TensorFlow operations, aggregations, and statistics on all of your raw features, and then put it in the correct format for TensorFlow to actually understand and train with. We then pass those features over to our training step, which happens in Vertex AI. And we currently just train on one server with multiple GPUs on it. And after training, the training step generates a model artifact. So that model artifact will be what eventually gets served in production. But also, we take that model artifact and we do an evaluation on it. So for our evaluation, we actually also use Dataflow. So in Dataflow, we can load in that model artifact as well as loading in a test data set from GCS, and then run inference on using that test data set with the model loaded into Dataflow. And then we calculate something called NDCG, which is basically just a metric to let you know how well your ranking model is performing. And the nice thing about this pipeline is every part of it is scalable. So as we get more data, as we get more traffic and more data, all of it just gets put into GCS. And then for our feature engineering and our evaluation, we can just up the number of workers to handle the additional traffic. And we are actually able to add workers to our GPU training, but we just haven't found the need for that complexity yet. Our training runs fine right now.
Yeah, very cool, Cung. Let's now bring it back to sort of the business benefits that you talked about.
Yeah, so to put quite simply, the benefit is just that search results are better. So one example is around personalization. So if you look at the screenshot on the left, this is what a new user might see. I basically just opened an incognito tab, and then I search earrings, and this is what I got. But then I started to click around on specific items. I started to add wooden things to my cart, add some rustic things to my cart, and I did the search for earring again. So on the right side, you can see the updated search results. So this is really catering to based on the user and what they're searching, we can show them what we believe they want to purchase. And this is also a benefit for the sellers in our marketplace because they get exposed to queries that they might have not been exposed to before. And overall, as we've run our A/B tests with our different models, we've seen increased search engagement and increased conversion.
Okay, very cool. Cung, thanks for sharing. Appreciate it. Hopefully the audience was able to get a sense for how you've done it and your journey. Thank you very much for your time. Appreciate it. I think. Oh yeah. So, are there any learnings or any takeaways that you want to leave with the audience?
Yeah. So the first thing I would do if you're looking to use ML. Is look into the research and the trends in your industry. I think this will help you hit the ground running and see what worked for other companies and then see the things that they struggled with. And also be prepared to fail. It actually took us about a year of iteration on our neural ranking model to get it to a state in which we felt comfortable putting it into production. So it can be a long process, but we felt the switch was worth it for all the benefits that came with deep learning and ranking. And then make incremental progress on your models and learn and iterate from when you run tests and things like that. And also, really important is to build your pipelines for scale. So understand where your data is now and where it might be in the future. Talk with your data scientists, your ML engineers, and your data engineers to decide on the right solutions for how to make ML models realistic for your use case.
Yeah, fantastic. Thanks, Cung. With that, I think we'll switch gears and talk a little bit about, let me do a quick time check. I think we've got maybe another 3-4 minutes. I'll do a quick rundown of all the latest and greatest capabilities, and then we'll open up for Q&A. We may not have enough time to take all questions, but we'll hang out by the side or outside the room, so please find us if you have questions. So before I go in and talk about the new capabilities, to give you a little sense for how we think about our roadmap and where we invest in, there are 3 key areas that the team is really focused on. The first is what we think of as best-in-class platform. This in my mind includes things like performance, scalability, reliability, and so on and so forth. This is the #1 reason why customers come to Google Cloud, particularly my product Dataflow. And this is an area that we continue to invest in. We've launched a number of capabilities in the last year. I've got a few that I'm personally very excited about that I'll quickly highlight. The second area, of course, is developer experience and overall usability of the product. Deploying, tuning, operating, and managing streaming pipelines requires a different set of tools than what you may have used for batch pipelines. So that's an area that historically we've invested in, and we've got a number of capabilities that I'll highlight today. And lastly, we want to make sure that, for enterprise customers like you, you're able to take our products, our platform, and integrate that into your IT systems, your IT policies, be able to meet your compliance needs, either from your own organization or regulatory compliance requirements that you have. So we've launched a number of capabilities like support for shielded VMs, support for confidential VMs, compliance with regulatory requirements, and so on and so forth. This is an area where we want to stay lockstep with your evolving needs as well. And then we talked about ML, that's sort of all pervasive, both in terms of giving you capabilities to do your own ML, but also applying ML to bring new experiences, new capabilities within the product. So with that, I'm going to quickly run through a few exciting capabilities. The first is something called dynamic threat scaling. This is very unique in the industry. We've been able to bring that from, if you recall, I talked about the product called Flume, which is used within Google. So we are able to bring this technique, which dynamically adjusts the number of threads that are scheduled per core. And the objective here is to really saturate CPU, reduce costs for you, and get the most amount of juice possible from the underlying resources. Right? Of course, we don't want developers to go hand-tune this, leads to a lot of operational toil. So we've got a system where we can dynamically adjust the number of cores that are scheduled, and then based on back pressure, adjust that as needed. Continuing on the theme of efficiency, some of you may know this. There's a component called streaming engine, which sits at the heart of streaming and data flow, which handles all of the stateful computations and streaming shuffle. There have been a number of techniques, a number of enhancements that we've rolled out to streaming engine in the recent past. I've highlighted some of those here, but most of those fall in the efficiency theme, right? How do we automatically tune the system based on your specific pipeline, based on your specific traffic pattern, so that we are able to optimize the infrastructure for cost, performance, latency, and things like that. On the developer experience side, remember I told you how deploying and managing streaming pipelines require a different set of tools. We've got a number of tools like our job graph, detailed dashboard, monitoring metrics. One of the things that you do not have until now is access to the actual data that was passing through your pipeline when a problem happened. Right? So we've got all sorts of visualizations and dashboards today where you can see where the problem occurred, but not what data was being processed when that problem occurred. So with data sampling, you now have an automatic capability where you're going to be able to see data that was passing through your pipeline when a problem happened. Again, to help with diagnostics and troubleshooting, that's an area where I see customers spend a lot of time, right? So straggler detection is an automatic capability that is going to identify hotkeys or, in general, elements that are slowing down your pipeline, automatically detect, and in some cases, not in all cases, in some cases, give you the root cause for stragglers and hotkeys in your data. This has been a favorite ask this year. While the billing data that is available as part of cloud billing is the authoritative source for cost information, I've had asks where customers want to give their individual practitioners the ability to quickly look up costs. So we've now launched job monitoring as part of the Dataflow UI, where you can get a sense for what the estimated costs for your jobs are going to be. With that, I'm going to skip a couple of slides. Actually, let me highlight this. One of our developers, published a cookbook that has close to 190 samples for a lot of common use cases. It covers both Python and Java. Do take a look at it, and he's looking for feedback and what else would be useful as well. It's all on GitHub. To wrap it up, a couple of other resources. There's a whole bunch of Dataflow ML notebooks, right, which you can just launch, hit run, and try it for yourself. And the second link, QR code, takes you to our Dataflow Get Started tutorials, where there are a number of tutorials, depending on whether you're new to Dataflow or you're an experienced Dataflow user. You could take those for a spin.